except we may not have used the word coordination other than in terms of coordinate covalent bond formation, which takes place when a Lewis acid-Lewis base reaction takes place. Because transition metal complexes, like all metal complexes, form as a result of Lewis acid-Lewis base reactions. Do you remember what a Lewis acid is? A species which supplies one or more empty valence orbitals, or has available one or more empty valence orbitals. Lewis base, a species which has the capacity to supply one or more pairs of electrons from its valence environment to make a coordinate covalent bond by taking occupation in one of these empty valence orbitals on the Lewis acid. So when the Lewis base uses a valence electron pair, most commonly a non-bonding pair, to take occupation in an empty valence orbital of a Lewis acid, you have a coordinate covalent bond being formed, and for the materials which we are presently considering, development of a coordination complex of a transition metal. So with that, you talked about the Mond process on Thursday. The Mond process is an aspect of chemical metallurgy, a process used to purify nickel. But what we are most concerned about regarding the Mond process is, as we've already noted, a springboard into the chemistry of these transition metal complexes. In so doing, you looked at the formation of this stuff by reaction of nickel in the zero oxidation state with carbon monoxide molecules. Well, molecules, of course, are always in a zero oxidation state because they have no charge. And what did you find out? You found out that not only is this stuff stable, it is, under normal laboratory conditions, a gas phase material. That, I hope, would immediately inspire you to say, something's unusual about this material. Because until now, or perhaps I should say until last Thursday, when you have seen formulas which contain, formulas for compounds which contain metal as well as non-metal elements, you have been looking at materials which have been ionic in character, at least substantially so. But if this material is gas phase under normal laboratory conditions, you should immediately recognize whatever it is, it's not ionic, it has to be molecular. Because you know that at normal laboratory conditions, all ionic compounds are crystalline solids. They all have high melting points or else a high temperature of decomposition, if they are composed of metal and non-metal elements. Well, this metal-non-metal compound is a gas under normal laboratory conditions. That means forming this compound by the reaction of nickel with carbon monoxide molecules is in fact a Lewis acid-Lewis base reaction. It is not a redox reaction, because the nickel maintained its zero oxidation state while the carbon monoxide molecules maintain their zero oxidation state, giving a material with a net zero oxidation state. So we've been reviewing why this can be argued as an interesting compound. The other aspect of this material, which is quite interesting, is the fact that it's got this metal in zero oxidation state. Because until now, all the metal, non-metal containing compounds that you've looked at have always been those in which the metal component has been in a positive oxidation state, and relative to the metal, the non-metal atom components have been negative oxidation states. Not here. Now, you presumably also talked about the fact that when nickel reacts with carbon monoxide to make this stuff, a rather unusual electronic property develops for complex nickel compared to free nickel. You remember what that unusual electronic property is? Here's 28 nickel. If we are to write the complete electron configuration for 28 nickel, we'd write argon core. That takes care of 18 electrons. And then what? 4s2 and 3d8. But I'm not going to write this argon 4s2 3d8. Even though that's the order in which the electrons were added to develop the configuration. I'm going to write this configuration 3d8 4s2 rather than 4s2 3d8. Why write it like this? Because as we have already recognized, and you learned this in 2045, when our electrons are lost by a species, like a nickel atom, and in so doing become converted to positive ions, which electrons leave first? Which electrons leave to develop the positive charge? The highest n value electrons always go first. Which means, as soon as I put electron density in the 3D sublevel, these 3D electrons become more stable, lower energy than the 4s electrons. Because if I start shooting energy at this thing to knock away electrons, these always go away first. Well, if these go away first, they must be easier to remove, they must be less stable. That's why I prefer to write the configuration like this. But back to this electronic property to which we were referring. If I use this kind of a diagram to sketch the valence electron configuration for nickel, a potential energy diagram, given that when two electrons occupy the same orbital, they must have opposite direction spins. This you know from 2045. Because the net paramagnetic character of any filled orbital has always been observed to be 0. So it must be that the spins of the electrons cancel each other. Result, no paramagnetic character for a filled orbital. But what about the nickel atom itself? Does it have paramagnetic character? Well, sketching the electron configuration for the 3D sublevel for nickel. All you got to do is follow the rules that you learned about in 2045. Hund's rule and the Pauli principle. These orbitals for the free atom are equal energy. So if we imagine putting in these 8 electrons on a one-at-a-time basis, we'll first half-fill each d orbital before we do this. Because when you have to put 2 electrons in the same orbital versus half-filling 2 orbitals which are equal in energy, it costs you more energy to put the 2 electrons in the same orbital. Pairing energy. You heard about this. The energy expense that you must deal with to get 2 electrons to live in the same orbital where they will be as close to each other as they can possibly be. Because electrons are each negatively charged. They repel each other. So you want to keep them as far from each other as possible when you're developing this configuration. So these 2 electrons are lower in energy than these 2 electrons. That's why you half-fill all the orbitals, given that they're all equal energy, before you start getting any spin-paired configurations. So the net d sublevel configuration for nickel is this, which means you got two half-filled orbitals, which means the nickel atom is paramagnetic. Now back to this unusual property, electronic property that we were referring to regarding this material. What happens to this paramagnetic character when this material is formed? Did you talk about this Thursday? Is this complex paramagnetic? No. Well, if it's not paramagnetic, then something had to happen to make these electrons pair up. Well, this configuration couldn't possibly be stable because this is a lower energy orbital than 4s. So as soon as I spin pair these two previously half-filled d orbitals, as if by magic, these remaining nickel valence electrons go from 4s back to 3d, because they're no more stable in 3d, since this is a lower energy sublevel. Now, this allows the 4 carbon monoxide Lewis bases, which transition metal chemists call ligands. A nice word, ligand. Almost sound mysterious. L-I-G-A-N-D. That's nothing but the transition metal chemist's name for a Lewis base. These carbon monoxide Lewis base ligands can each supply one non-bonding pair per carbon monoxide molecule. Coming from which end of the molecule? You did this Thursday. Is it the case that sometimes carbon monoxide uses this non-bonding pair to make a coordinate covalent bond, sometimes this non-bonding pair? What did you find out on Thursday? Always uses the non-bonding pair from carbon. Isn't that reasonable? Carbon is of lower electronegativity than oxygen, considerably so. Plus, formal charge analysis of this CO molecule shows you something quite unusual. The formal charge distribution is minus on carbon and plus on oxygen. That's not the way we prefer to have the formal charge distributed. If possible, we prefer to have negative formal charge, if there is any, on the atom of greater electronegativity. But such is not the case for carbon monoxide. Because the bottom line dictator for this case is the realization that there is, in fact, a strong triple bond maintaining the structural integrity of this molecule. So you have no choice but to write the Lewis structure so as to keep with this triple bond. And of course, in writing Lewis structures, since you got 10 valence electrons total for a carbon atom and an oxygen atom combined, the only Lewis structure you could write, with each atom appearing to be in an octet after you write the Lewis structure, is this, which keeps with the triple bond. So not only is carbon of lower electronegativity, thereby making it a better electron density donor than oxygen, it's also an atom which has got a minus formal charge, showing you that this atom is more minus, electronically speaking, than oxygen. All keep with why, when carbon monoxide behaves as a ligand, it uses only and exclusively in forming the sigma bond, non-bonding pair from carbon, never the non-bonding pair from oxygen. So, here come our 4 carbon monoxide molecules. Each supplies a non-bonding pair. What are the empty valence orbitals in which these 4 non-bonding pairs total will take residence? For S and 4p sublevels respectively. Because after this spin pairing took place, when carbon monoxide molecules made bonds with nickel to make this stuff, you freed up the 4s orbital. You need 3 more. The next available empty orbitals in terms of energy would be 4p, which allows us to realize for this stuff, our analysis tells us that the nickel atom is sp3 hybridized, because these are the orbitals which were occupied by the ligands, carbon monoxide molecules, when they made the coordinate covalent bonds, 4 of them total. S, P, 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 sp3. What kind of geometry do you associate with sp3 hybridization? What is it? When each of these sp3 sigma pairs is used to make a bond? Tetrahedral. And guess what? That's correct. Plus, this thing is diamagnetic, not paramagnetic. And this analysis shows us that after this bond formation interaction took place, nickel lost its paramagnetic character. Nickel, the free atom, is paramagnetic. Nickel, the complexed atom, in this stuff, is diamagnetic. Interesting, isn't it? So, we go to the next part of this analysis. Question 2365, which reminds us that if you count up for nickel in this material, the total number of valence electrons, you got 18. And what we find out by observation and experimental investigation, when we make these complexes of transition metals, with the metal being in an unusually low oxidation state like 0, the complex metal invariably has a total valence electron count of 18. So like we did in 2045, you expect atoms to react so as to achieve a total valence electron configuration which is equivalent to that of nearest neighbor noble gas. Well, we're going to play that game again. Except that when we look at the period 4 transition metals, which are called the first row transition metals, because period 4 is the first row that contains transition metals, scandium, titanium, vanadium, etc., all the way down through carbon, copper, never mind zinc, that's not really a transition metal. We'll talk more about that in a moment. These are the first transition metals which you'll encounter in the periodic system. First row, but they live in period 4. And their nearest neighbor, noble gas, is krypton. When these transition metals behave as electron receivers in forming coordination complexes, because the complex metal behaves as a Lewis acid in forming these complexes. So we're going to use this as a device when we consider the possible stability versus instability of a complex of a transition metal where electron configuration analysis tells us the transition metal is in an unusually low oxidation state. Does the metal in the complex have 18 valence electrons? If it does, we can expect the complex to be stable. But if it does not have 18 valence electrons like krypton, then we will not expect the complex to be stable. And to the best of my knowledge, there are few, if any, exceptions to this interesting rule. So I wrote, as a verification of this statement we just considered, nickel tetracarbonyl, tetra because you got 4 of them, exists stable, but species such as nickel tricarbonyl, nickel pentacarbonyl, etc., these don't exist. In this material, the number of valence electrons for nickel would be 60. Here, 20. Don't exist. So, this gives us a reason to believe that this krypton valence electron configuration analogy is a useful device, a valid device. So with that, let's go to 2367. A carbonyl complex of iron in the zero oxidation state. What's the value for X that you predict? Many of you likely did this on Thursday, but the review won't hurt. On the other hand, all the discussion classes didn't make the same degree of progress, and I want everybody to get the same foundation for this stuff. Well, there's iron number 26. Reminder, to play this game, to understand transition metal coordination chemistry, it will almost always be the case that in short order fashion you need to be able to identify the valence electron configuration for the complex metal. How are you going to do that? You start with the free metal. And after you start with the free metal, you will determine the additional electrons which have been added to its electron environment by complexation. And when you put these two parts together, you'll be able to determine the oxidation state for the metal. Iron, 26. The iron atom all by itself. How many valence electrons?
8.
8. All right. And in this material, iron has retained its zero oxidation state. So in forming this material, iron itself has contributed 8 valence electrons to the total valence electron configuration for complex iron. Well, it doesn't take a lot of fancy arithmetic to realize that if we want to get to 18, how many more valence electrons do we have to add to iron? 10. So how many sigma bonds do we have to make? 5. Because each sigma bond constitutes the addition of an electron pair to the valence environment of the metal. And if each carbon monoxide molecule in bonding with iron contributes 1 electron pair, then how many carbon monoxide molecules do we have to have interact with iron to give us a stable complex? 5. Nothing fancy about this. So, given that this is correct, what's the hybridization of iron? Well, let's go back to this diagram, except now use it to simulate iron rather than nickel. So there's iron all by itself, 3d6 4s2. So before complexation, in this case by carbon monoxide molecules, here's the 3D configuration for iron with 2 electrons in 4s. Now what happens to these 2 electrons in 4s? What happens to these half-filled orbitals when iron interacts with the CO molecule? Well, the answer to that question comes from taking this stuff in the laboratory and doing some experiments on it to observe that this stuff, like this stuff, is diamagnetic. Well, then iron, just like nickel in forming that, experienced a rather serious change in its valence electron configuration on complexation with carbon monoxide molecules. Spin pairing, and the 4s electron pair becomes a 3d electron pair. Almost like magic. But we believe this magic because of the observed properties of this stuff. That's why we believe it. The facts dictate that we should believe this. Well now, here's what the 3D configuration looks like for iron after complexation. There's the 8 valence electrons, except now they're all spin paired. So what orbitals are now available for occupation by 5 carbon monoxide molecule non-bonding pairs when this complex is formed? 3D, 4s, and each of the 3p orbitals in the 4p sublevel. Because this time we got to make 5 coordinate covalent bonds. Well, we made them. Count up the electrons, we got the magic number of 18. What's the hybridization? The hybridization, you should have got this in 2045, but I don't know. The hybridization is always identified by the orbitals which were occupied by the electron pairs that came from the ligands. 3D, 4s, and 4p times 3. So we'll call it DSP3. 1D, 1s, and all of the p's. Don't read this as DSP cubed. Read it as DSP3. What kind of geometry do you associate with DSP3 hybridization? Now, in 2045, I don't believe you looked at DSP3 hybridization, but I believe you looked at SP3D hybridization. What do you think the difference is between DSP3 hybridization and SP3D hybridization? You got the same mixture of orbitals, but what's the difference? Tell me, for iron or any transition metal atom from period 4. Beside the 4p sublevel being there and being empty, what other sublevel is part of the valence environment but is empty? 4s, 4p, what's next? Part of energy level number 4. 4d! Nothing fancy about that. So the 4d orbitals are empty, but present for all transition metal atoms in period 4. Now, in constructing this hybrid, did I occupy an energy level 4 d orbital? No, I occupied an energy level 3 d orbital. An orbital which is lower in energy than 4s or 4p. So I write the hybridization scheme like this. DSP3. Because in constructing this hybridization scheme, I've used the d orbital, which is lower in energy than the s and p orbitals, because the d orbital is from energy level number 3. But if instead this sublevel was filled, and I used 4s, 4p, and whatever the required number of orbitals from 4d to make the hybrid, then I'd write this. It's just a way to identify the energy of the d orbital that's part of the hybrid relative to the energy of the s and p orbitals, which are part of the hybrid. This means the d orbital is lower energy, has a lower quantum number than the s and p orbitals. This means the orbitals all have the same quantum number. They're all from the same energy level. And in a given energy level, S is more stable than P, which in turn is more stable than D. So that's all this means relative to this. And when we get further into this, you'll learn that this kind of a hybridization scheme corresponds to an inner orbital complex, and this corresponds to an outer orbital complex. Language. No more, no less. More on that later. All right. We know 5 is the correct number. We know the hybridization is DSP3. Geometry? Shape? What's the shape you found for sp3 hybridization? 2045. Provided every sp3 electron pair is bonding to a peripheral atom. Trigonal bipyramid. Or trigonal bipyramidal if you want to use it as an adjective. This is trigonal bipyramid. All stuff we've seen before. It's just that now we're applying it to types of compounds that we haven't seen before. All right. We proceed. Let's play this krypton configuration, valence configuration analogy game again. I've given you here 3 suggested possible carbon monoxide complexes of cobalt. I trust you realize this. In 2046 laboratory, assignment number 2, if you can remember back that far, you made some interesting precipitates of ammonium ion and potassium ion with cobalty nitrite complex anion, cobalty nitrite. When I have taught that laboratory course, I found a number of students writing the formula for the cobalty nitrite anion using capital C, capital O. I always would take my red pen and just go X, send them back. Because I'm not going to let a student of chemistry tell me that cobalt and carbon monoxide are the same species. They sure as hell are not. Damn it. So we proceed. Which of these do you predict to be the stable carbon monoxide complex of cobalt? The positive ion, the neutral species, or the negative ion? The anion. Why? What's that?
The extra electron against nickel's electron configuration. I think only needs 4.
Cobalt by itself, 27 electrons. How many are valence? 9. So how many more electrons do we have to pop into the valence environment of cobalt to develop an 18 electron configuration for the valence level? 9 more. Well then, since our ligands are supplying electrons in pairs, that means we've got to add another electron to the metal. And when you add an electron to something that's neutral, it becomes negatively charged. So how about that? Here's the stable stuff. What's the oxidation state for cobalt in this stuff? What is it? -1. More interesting stuff. Not only have we seen stable materials with metals in zero oxidation state, now we're seeing a stable material with a metal in a negative oxidation state. I'm sure a metal property you've not yet observed before. What's this remind us about? Reminds us that with coordination chemistry, you can achieve a lot of very interesting and unusual behavior. And oftentimes extremely important behavior. A couple of examples of which we've already reminded you. Chlorophyll, a magnesium complex. You think chlorophyll's stable? I mean, unusual and important? With chlorophyll, these little green plants can rupture nitrogen molecules. Break up that nitrogen-nitrogen triple bond, which is damn strong and which is awful hard to do by chemists in the laboratory. But the little green plants can do it with the assistance of chlorophyll and make available nitrogen atoms from which they synthesize amino acids and thereafter proteins. Based on chemistry as we understand it, without chlorophyll, we wouldn't be here talking about this kind of stuff. Hemoglobin, a complex of iron in the +2 oxidation state. What's the main function of hemoglobin in the body?
Transportation of oxygen.
Oxygen transport, one way, and then CO2 transport the other way, after the oxygen has been metabolized. All right? 2369. A complex of iron containing carbon monoxide molecules and a very interesting cation, NO+. I think it's nitrosonium ion by name, but I don't care about the name. We'll just call it NO+. Right now on your paper, write the Lewis structure for this NO+ thing. And after you write this Lewis structure, I would like you to offer a scientifically sound comment on the bond strength between nitrogen and oxygen in NO+. Do you see anything about the valence electron configuration for NO+, which bears a striking resemblance to the valence electron configurations of these two species? What do you see? Triple bond. Well, if you're going to write a Lewis structure, what do you do first? You count the number of valence electrons. How many you get? 10, just like these. And when you finish this Lewis structure, you find out the only Lewis structure you could write, which would provide the appearance that nitrogen and oxygen are each in a valence octet, would be this one. How many got this one? Nothing fancy about this, not difficult. Now here, the formal charge for the species is on oxygen, as it is here. Again, unusual, because nitrogen is of lower electronegativity than oxygen. But we talked about carbon monoxide behaving as a ligand, and in so doing recognized that when this thing behaves as a ligand, it uses only the carbon non-bonding pair, never the oxygen non-bonding pair. How do you think this thing behaves as a ligand? This? This? Both? What do you think?
Yes.
When this behaves as a ligand, can it be expected to use the nitrogen non-bonding pair only, the oxygen non-bonding pair only, or serendipity? Sometimes this, sometimes that. How do you vote? Nitrogen non-bonding pair only. Oxygen non-bonding pair only. Serendipity. How many didn't vote? Carbon is of lower electronegativity than oxygen. Nitrogen is of lower electronegativity than oxygen. That tells me that nitrogen or oxygen is more willing, so to speak, to share its non-bonding pair to make a bond. Nitrogen. Is this atom more negative than this atom? Well, this atom is plus. This atom hasn't got any charge, so it's got to be more negative by default. The only non-bonding pair ever used by this unusual cation is the nitrogen non-bonding pair. Just like the only non-bonding pair used by carbon monoxide when it does its coordinate covalent bond formation thing is the carbon non-bonding pair. All right? Now then, in the world of chemistry, it is known as a fact. This is the third strongest bond interaction known. Counts for why the nitrogen molecule is so stable. This is number 2. And there's number 1. That's the strongest bond interaction known in the world of chemistry. Why do you expect this NO triple bond to be stronger than the CO triple bond? Which in turn is stronger than the NN triple bond? What property of an atom in the bound state measures its ability to stabilize valence electron density? What is it? What is it? Electronegativity. When we started this conversation on, for example, rationalizing stabilities of Bronsted acids, didn't we have to pay attention heavily to electronegativity? And at that time, did I ask you to write a definition of electronegativity? I did. I don't know how many of you wrote it. I'd hate to have to live on the money I'd get from a show of hands. The combined electronegativities of nitrogen and oxygen exceed the combined electronegativities of any two atoms from the other two molecules. Well then, if the combined electronegativities of nitrogen and oxygen is the greatest, then the bonding electrons for NO plus are stabilized to the greatest extent. Which is why that bond, triple bond if you prefer, is the strongest known bond in the world of chemistry. One, because it's a triple bond, and number 2, no other species shows a bond order of 3, or a bond order as great as 3, with a combined electronegativity for its constituent atoms that exceeds that of nitrogen and oxygen. You'll see more about this in chapter 25. We'll say something about that later on. All right, 2370. Metals in unusually low oxidation states. That's all we've been talking about so far. What have we found out about these metals? They're in 18 electron valence environments, analogous to that of krypton. What have we found out about these complexes and their magnetic character? Diamagnetic. Because bond formation interaction with the ligands on complex formation leads to driving the valence electrons for the metal itself into lower energy orbitals, which causes this spin pairing, resulting in diamagnetic character for the complex. Now, tell me, have you before come across DSP2 hybridization? I'm just asking. DSP2 hybridization corresponds to square or square planar geometry. We'll talk more about that in a coming conversation. But regarding DSP2, for a period 4 transition metal, this leads to occupation for a period 4 transition metal of a 3D or 4D orbital. We talked about this a moment ago. D before S and P. What? 3D, 4S, 4P, but how many of them? 2. So I repeat. Can we expect a complex with a metal in an unusually low oxidation state to be stable and show square planar geometry? Yes or no? Why not? I don't give a damn about your vote. You know that. If we have DSP2 hybridization, which of these orbitals for a period 4 complex transition metal, which of these orbitals are occupied by coordinate covalent bond electron pairs? The electron pairs which were supplied by the ligands. If we got square planar geometry, how many ligands? 4. One 3D, 4S, and 2 of the 3 4Ps. The hybrid scheme tells us that. Where are the metal electrons? Of course, they're all metal electrons now. But the electrons which were initially belonging only to the metal, there they are. How many valence electrons we got? Count them. 16. Is that 18? Let me get out my calculator and see if I can find out. As soon as you have a hybrid scheme which shows an unoccupied valence p orbital, you cannot possibly have